Hello student, in this video I am going to start from the last point we have discussed regarding the curve representations. So today I am going to discuss about few other topics regarding the curve representations. Here starting with Bezier curve. So in case of Bezier curve, here you can see this is a curve, or this might be a curve. To draw this curve we use some control points. Here P0, P1, P2 or P3, these are control points. And here you can see there are three segments of edges. So segments, and those are the sides of a polygon, and those are the control points. So if there are n number of segments, there will be n plus 1 vertices, or you can say a number of control points, and that is used by like this equation, summation of pi, that number, that control points, okay, bin u, function of the Bezier curve. U is the parametric variable, which is the values of u is from 0 to 1. So this is just the equation for Bezier curve, where P is the control point and there is n number of control n from 0 to n, that is why n plus 1 number of vertices are there, okay, from 0 to n, and there are n number of segments of polygon sides, or you can say lines, and that Bezier curve B function is related with the parametric variable u, and that value of the variable lies between 0 and 1. So Bezier curve, P. Bezier, the French automobile company of Renault, first introduced this Bezier curve. So a system for designing sculptured surfaces of automobile bodies based on the Bezier curve, which passes P0 and Pn two endpoints. There are two endpoints, P0 and it is named as Pn, but here you can see P0 and P3. These are two endpoints. Has endpoint derivatives. So it might be P0 and P1 also, P1 and P2 also, P2 and P3 also. So here endpoint derivatives are like this: P0 dash equal to n into P1 minus P0. So difference between two points uses a factor of control points representing the n plus 1 vertices of characteristics polygon. So this is the derivative used, this is derivation used to find out that curve. So actually it follows like this. This is the equation, this is the factorial equation, okay. So from I equal to 0 to 1 to like that, for that is the equation. Here you can see that if n equal to 2, if the number of points is 2 or segments is 2, bi and u is a function of number of curved segments. So you can use these equations. So here if you put the values of n, okay, n is 2 for every case, but I will be changed, so if we change the i's, you will get the values like 1 to 1. So that is to find out the polynomial, Bernstein polynomial. We need to find out the polynomial. In the mathematical field of numerical analysis, Bernstein polynomial, named after Sergei Natanovich Bernstein, is a polynomial in the Bernstein form, that is a linear combination of Bernstein basis polynomials. A numerically stable way to evaluate polynomials in Bernstein form is de Castel-Yau's algorithm, which reduces the computational demand caused by factorials. I just giving you these slides and details, but no need to give too much emphasis on these mathematical explanations. Just understands how we can draw this type of things, what are the important factors associated with this. Here again one example, suppose n equal to 2, and that is why there will be n plus 1 vertices, and that is how this is the same thing here it is showing. So this is the equation that is shown initially. This is the equation. So, and this is the equation of this Bernstein polynomial. So now Pu for any point 1 into 1 minus mu square P naught plus 2 into mu into 1 minus u P1. If you use that equation here, and you do the do the explanation, 2 into mu into 1 minus u into P1 and 1 into u square into P2. So this is just the expansion of these equations. And P naught, that is derivative, P naught is, that is one, P naught is this one. So P dash, sorry, P dash, this is the P dash. So for any P dash you will get this one. This is the derivative of this, so we can get this one. Then if you put 0 in case of u, you will get this one. P0, if you put 0 here, you will get this one. If you put 1 here, you will get this one. If you put 0 in this equation, you will get this one, this one. So here P naught, the order of Bezier curve is a function of the number of control points. So here the order of the Bezier curve, this is the important part here, is order of the Bezier curve is a function of the number of control points. For control points, n equal to 3 means segments of line is 3, always produce a cubic Bezier curve. This is a cubic Bezier curve, always produce that type of Bezier curve. This is also a cubic Bezier curve. These are cubic Bezier curve. Okay. So if the control point number is 4, or you can say a segment of line is 3. Again, another thing is that convex hull property. In addition to the properties of Bezier curve described previously, another important property of Bezier curve is the convex hull property. A convex hull of a Bezier curve is a convex polygon formed by connecting the control points of the curve, as illustrated by the hatched areas in the figure. Note that each of these Bezier curve resides completely inside the convex hull. So here you can see, if we join the polygon, then whole curve remain inside that polygon. That is what it is saying. A convex hull of a Bezier curve is a convex polygon formed by connecting the control points of the curve, as illustrated by the hatched areas in hatched figures in the areas. Note that each of these Bezier curve resides completely inside the convex hull. Another example, the coordinate of 4 control points relatively concurrent WCS are given by P0 to 20, P transpose P1 to 230. That is the point value, XYZ value. P2 is this one, P3 is this one. Find the equation of the resulting Bezier curve. Also find points on curve for mu equal this. Means this is the value of mu u. So these are the control points P0, P1, P2, P3. So solution is that our equation will be like this: P0, B0, here P0, this is the first control point. So B0 will be B0 and 3, B1 and 3, B2 and 3, B2. This is B33. This should be B33. And in that way, equation of B is this one, and equation of Pu is this one. And because this is following cubic polynomial, if you put that thing here in this equation, you will get the same thing. This is for square, that is why like this, but if you put cube, it will become like this. cube, square, square, cube. And here you can see b naught 03 is 1 minus u cube. So p naught is this one. P naught means if you put p naught here, if you put p naught here, 0, and p0, p0, that is 220. P naught, if you put 0, you will get 220 directly. If you put 1 by 4, 1 by 4 in this equation, 1 by 4, then you will get this equation, and you can put the values of p naught, that is this one, and this one in here, and by summing the matrices you can get this. So in that way, by putting the value of, these are the values of u, 0, 1 by 4, this is the values of u, 0, 1 by 4, 1 by 2, 3 by 4, and 1 by 4, 1 by 2, 3 by 4, and 1. And p naught will obviously 220, and p1 will be 320, because that is a starting point, this is the ending point. And here this is 220 means 2 2 and 0, this is 320 in 2 dimension we are showing, that is a 0 in the third dimensional value. And this is 2.156 almost, and 2.563 almost 2 and 3, that is a 2 and 3, and this is 2, this is 3 3, this is 3 3, and p3 by 4, that is this one 3, this one, but this has not been shown here. Control points are this one, but actual points are here, okay. Control points are p1, p2, p3, p4, and points on the curve is pu for 1 by 4, 1 by 2, 3 by 4. Here these are the control points, that is why this is the control points, and using those control points we have found these points. So you can again try to understand this by following the equations, okay. Improvement of Bezier curve over the cubic spline. The shape of Bezier curve is controlled only by its defining points. So we can only control the Bezier curve using the control points. First derivatives are not used in the curve development as in the cubic spline. The order or the degree of the Bezier curve is variable and is related to the number of points of defining it, that is the controlling points, and the degree of the curve. This is not the case of cubic spline where the degree is always cubic. So in case of cubic spline, the degree of the polynomial might not be always cube or 3, but in case of here this is fixed. The Bezier curve is smoother than the cubic spline because it has higher order derivatives. Next is B-spline. So we'll try to discuss this about B-spline in next video. It will take some time, that is why. And main important part of today's video is this part. This is a simple solution how we can go through, and just you need to understand this process, this equation first, okay, and this equation. But you might not go through this equation also, you can directly understand this one and this one, and you just put the values of u is given here, and the values of p naught, p1, p2, p3, and that can be get from this equation, and that is the values of u. And by putting the values of u and putting the values of p naught and p1, p2 and p3, we can values of that points, that green points. These are the green points values, and this is the actual control points which has been given in the questions. So try to do this example Most importantly, you need to understand this part, this equation first, and how we have got this equation or how that is used from here. This is part, and this way we can go through. You need to understand how this can be get by using the derivatives. Okay, by using the calculus forms, equations or explanations or derivations. So that is why I try to give this hint. Just try to understand this, only this example. No need to go for more explanation or more understanding about the mathematics part. But if you also have want to know something more about these things, you can go through literature also, or if you have any doubt also, let me know. We'll try to resolve those doubt over Google Meet. That's it. Thank you.